In this lecture, we are going to discuss about combined effect of variable normal and shear stresses. So the Soderberg equation is 1 by n sigma m by sigma y plus kf sigma a by sigma minus 1. To get the equivalent stress equation, I am going to multiply sigma y throughout the equation. So it is sigma y by n is equal to sigma m by y into sigma y will be there. Sigma y will get cancelled plus kf sigma a sigma y divided by sigma minus 1, that is equal to sigma equivalent. So the sigma equivalent is equal to sigma m plus kf sigma a sigma y divided by sigma minus 1. So this is the equivalent stress equation for axial and bending stresses, that is for normal stress. In the case of shear stress, tau equivalent is equal to same, in the place of sigma it is replaced by tau. So tau equivalent is equal to tau m plus kf tau a tau y divided by tau minus 1. So this is the equivalent stress equation for torsional shear stress. Now if we have axial and bending combination, then initially we have to calculate the equivalent stress for axial using the formula which I have shown, and then the equivalent stress for bending. So further we have to add these two equivalent stresses, then we have to equate this to sigma y divided by n to find the diameter. So just like the combined stress problem, in the case of axial and bending we have to add it to find the diameter. In the case of axial plus torsion or bending plus torsion, so this is the equation to find the diameter. So 1 by n is equal to sigma equivalent divided by sigma y the whole square plus tau equivalent divided by tau y the whole square the whole power 1 by 2. In the case of axial and bending, then sigma equivalent is because of the axial load. In the case of bending and torsion, then sigma equivalent is because of bending and tau is for torsion. So all these formulas are there in the data book page number 7.6. So this is for sigma equivalent. So sigma equivalent is equal to sigma m plus kf sigma a sigma y divided by sigma minus 1. So similarly for tau equivalent. Further, this is the equation for combined stress, that is normal plus shear stress. Okay, so this equation should be used when we find a combination of normal and shear stress in the problem. So we'll start with the axial and bending combination. A cantilever beam of circular cross section whose length being 200 mm is subjected to a transverse load and an axial load as shown in figure. Determine the required diameter using a factor of safety of 2. The strength properties are: ultimate strength is 500 megapascal, yield strength is 400 megapascal, endurance limit is 250 megapascal. Stress concentration for bending and axial loads are 1.4 and 1.6 respectively. Take size factor as 0.8 and surface finish factor as 0.9. So this is the given drawing. So the first step is to split the problem into two parts. So the first part is bending load and the second part is axial load. Okay, so we'll write the given data. First we'll write the common data. So sigma u is equal to 500 Newton per mm square, sigma y is 400 Newton per mm square, sigma minus 1 is equal to 250 Newton per mm square. Then size factor is given SZ and surface connection factor is 0.9 and the factor of safety is given as 2. Now for bending, so considering the bending load alone, the minimum load, you can see that for bending two loads are there. So one is 50 Newton and the another one is 150 Newton. You can see the image. And we know that for bending and axial load, the minimum load should be considered in negative direction. So I am going to write W minimum for bending is minus 50 mm, 550 Newton. Then for W max, it is 150 Newton. And here you can see the stress concentration for bending and axial loads are 1.4 and 1.6. So this 1.4 is for bending and this 1.6 is for axial load. Okay. So Kf for bending is 1.4 and in the case of axial Kf is equal to 1.6. Now coming to the axial load, two loads are there. One is 100 Newton and the another one is 400 Newton. We know that for axial the minimum is negative direction. So P minimum is equal to minus 100 Newton and P maximum is equal to 400 Newton. So one part of the problem is bending and the another part is axial. So first we have to calculate the sigma equivalent for bending load and then we have to calculate the equivalent stress for axial load. So finally after calculating the equivalent for bending and axial, then we can use the combined variable load equation to find the diameter of this given shaft. So we'll first consider the bending alone. Consider bending and we know that for bending and axial sigma equivalent is equal to sigma m plus kf sigma a sigma y divided by sigma minus 1. So this equation is in the data book page number 7.6. At the bottom of the page you can find that combined stress equations. Okay. Here sigma m is mean stress. As we all know, mean stress is sigma max plus sigma minimum divided by 2 and sigma a is sigma max minus sigma minimum divided by 2. So here sigma m we should calculate, sigma a we should calculate, kf for bending it is given, sigma y is also it is given, the endurance limit stress is also given. Okay. So we'll calculate the sigma m and sigma a. The maximum stress. We know that for bending the maximum stress equation is 32 m max divided by pi d cube. In the case of maximum it is max. In the case of minimum it is 32 m minimum divided by pi d cube. Okay, fine. So first we have to calculate the maximum and minimum bending moment. The given beam is a cantilever beam. So the bending moment will be load into perpendicular distance. So for maximum bending moment it is W max into L, that is the maximum load is 150 Newton and the length. Okay. So we have already solved a problem on stepped shaft subjected to bending loading and we know that the maximum stress will be accumulated at the fillet region. So we have to consider the smaller diameter length alone. So we should not consider the overall diameter. We have to consider to 200 mm. So W max is 150 and it is 200. So it is 30 into 10 power 3 Newton mm. In the case of minimum bending moment, M minimum is equal to W minimum into L. W minimum it is minus 50. It is given in the problem and the length is 200. So we will get minus 10 into 10 power 3 Newton mm. So we can substitute the maximum and minimum bending moment values in this equation and we can find the maximum and minimum bending stress. Further we can substitute the maximum and minimum bending stress in the mean and variable stress equation. The mean stress is maximum plus minimum. So here you have a negative direction in the minimum stress. So you will get 101.85 into 10 power 3 divided by d cube. In the case of variable stress, it is maximum minus minimum. So already a minus is there. So minus and minus will become plus. So you will get 203.71 into 10 power 3 divided by d cube. So now we can substitute everything in this equation. Sigma m we have calculated, it is 101.85 into 10 power 3. I have substituted it. Kf it is given in the problem. You can see that it is 1.4. Then sigma a we have calculated, it is 203.71 into 10 power 3 divided by d cube. Sigma y is the ultimate strength. It is given in the problem. Then KSR and KSZ is given, it is 0.9 into 0.8. So actually KB will be there, okay, the load correction for bending, and we know that KB is equal to 1. The load correction factor for bending is equal to 1. So we can substitute that. And the endurance limit, it is directly given in the problem, it is 250 Newton per mm square. So by solving everything, then finally you will get sigma equivalent is equal to 735.61 into 10 power 3 divided by d cube. So this is for bending. So now consider the axial load. Use the same equation, sigma equivalent is equal to sigma m plus kf, sigma a, sigma y divided by sigma minus 1. So here also sigma m we have to calculate, kf is given, sigma a we have to calculate, sigma y it is given, and the endurance limit stress also it is given. So we'll calculate the maximum and minimum stress. Since it is axial load, the formula for maximum and minimum load is W divided by A. It is load divided by area. In the case of maximum stress, it is W max divided by A. In the case of minimum, it is W minimum divided by A. So substitute the value of W max, it is 400 Newton, and the shaft is circular cross section. So the area is pi by 4 d square. So you will get 509.29 divided by d square. In the case of minimum stress, substitute the minimum load, that is minus 100 Newton. So you will get minus 127.32 divided by d square. So now substitute the maximum and minimum stress in the mean and variable stress equation. So the mean stress will be 190.98 divided by d square, and the variable stress is 318.31 divided by d square. Now we can substitute everything in this equation. Sigma y we have calculated, it is 190.98 divided by d square. Kf is given in the problem. For axial, the Kf is 1.6. So you can substitute that. Then sigma a it is given, it is that we have calculated. So 318.31 divided by d square. Sigma y it is given in the problem. You can see that, here it is 400 Newton per mm square. Then here the correction factors. So Ka is the correction factor for axial load. Okay. So we know that Ka is equal to 0.8. For axial it is 0.8. Further, KSR and KSZ is given in the problem. It is 0.9 and 0.8. The endurance limit stress is also directly given. You can substitute that. It is 250 Newton per mm square. So by solving this equation, you will get sigma equivalent for axial load is 1605.7 divided by d square. Okay. So we have calculated the equivalent stress for bending and axial load. So now we have to combine these two equivalent stress values. So this comes under case 1, that is axial and bending. So we can add the two equivalent stresses to calculate the diameter. So the equation is sigma y divided by n. So this equation will not be there in your data book. Just remember this equation. Sigma y divided by n is equal to sigma equivalent for axial plus sigma equivalent for bending. So sigma y is given in the problem, it is 400, and the factor of safety is 2. Sigma equivalent axial we have calculated. Sigma equivalent bending we have calculated. So you can substitute that. Okay. Now I am going to bring this 400 by 2 to the left hand side equation. So this is the equation you will get. So now we have to solve this equation. Okay. So we can solve this equation by multiplying the d cube throughout the equation, so that we can easily solve the equation. So it is 1605.7 into d cube. Already d square is there. So d square and d square will get cancelled. You will get 1605.7 d. Then here d cube will be cancelled. So you will get 735.61 into 10 cube. Then 400 divided by 2, it is 200 into d cube, that is equal to 0. So now this is the equation. So you can solve this equation using your calculator. In the calculator, go to equation mode and the degree is 3. Okay. So degree is 3. In the calculator, this is the a value since it is d cube. And there is no d square is there, so b is equal to 0, and this is the c, and here it is d, that is equal to 0. So after solving you will get 3 values, and from the t values take the positive value. So the remaining 2 values will be in the negative, so take the positive value. The d is equal to 15.6 mm. Okay. So this is how we have to solve this equation. So first you have to calculate the combined stress for bending, then equivalent stress for bending, then equivalent stress for axial, and further you can add the equivalent stresses and you can equate with the sigma y divided by n. So this is how you have to solve the problem. Now the tutorial problem. A steel cantilever is 200 mm long, is subjected to an axial and a transverse load as shown in figure. Determine its diameter taking a factor of safety of 2. So n is given. Assume the following values. Yield stress is given, so sigma y is directly given. Endurance limit is given, so sigma minus 1 is given. The correction factors. So these are all the load corrections factors. So Kb is 1, so for bending it is 1, and for Ka, so generally we will take 0.8, but here in the problem they have given us 0.7, so you can take the Ka value as 0.7. Then the stress concentration factor. So Kf for bending is 1.44, and in the case of axial, Kf is 1.64. Then the size factor and surface factor values are given. Now coming to the drawing, so it is also a stepped shaft subjected to both axial and bending load. So here the axial load varies from 150 Newton to 450 Newton. So the minimum load is minus 150 Newton and the maximum load is 450 Newton. In the case of bending, the minimum load is minus 80 and the maximum load is plus 120. So while calculating the bending moment, so the load into the distance is 150 mm, not 200 mm, because the stress concentration will be there at the fillet region. And while calculating the axial stress, so it is load divided by area, so you will have pi by 4 d square. Okay, so you should put the smaller diameter value. So this region you should consider because the magnitude of stress will be higher at the lower cross section. Okay, so here the stress concentration will be high comparing with the 2D diameter. Okay, so these two things should be kept in your mind while solving the problem. So first consider the bending load alone and calculate the sigma equivalent for bending. Then consider the axial load and calculate the sigma equivalent for axial load. Finally, you can add these two sigma equivalent values and you can equate this to sigma y divided by n and you can find out the diameter value. So the diameter value will be around 12 mm.